This is Unit 4, Bonding. Chemical bonds. What is a chemical bond? A chemical bond is what holds atoms together. Bonds are formed by the attraction of the positive nucleus of one atom to the negative electrons of another atom, or by the attraction of positive and negative ions. So, when two or more atoms give, take, or share electrons. Are there different types of bonds? Yeah, there's 3 different types of bonds: ionic, covalent, and metallic. The bonds are determined by the difference in electronegativity. Remember the Pauling scale? When there is a small difference in electronegativity, or no difference, this is a nonpolar covalent bond. When there's a medium difference, the electrons are shared but not equally, so this is a polar covalent. And if there is a large difference, the electrons are given or taken away, and this is ionic bonds. What are ionic bonds? Ionic bonds have one cation and one anion. Electrons are given or taken away. So ionic bonds occur when there is a large difference in the electronegativity of one atom, and one atom is going to take the electrons from another one. One ionic particle is called a formula unit. The electrons are not shared, but the particles are held together by the opposing charges, or electrostatic forces. So what are the properties of ionic bonds? Ionic compounds form regular repeating patterns or a crystal lattice. They are hard, brittle solids with very high melting points and boiling points. Ionic compounds in the liquid states or in solution can conduct electricity. What are covalent bonds? Covalent bonds result from the sharing of electrons between two nonmetals, kind of like a tug of war with the electrons. Are electrons shared equally? Not always. There are polar and nonpolar bonds. Nonpolar bonds form when nonmetals share electrons equally, because the electronegativity of the atoms, the two atoms, is similar or the same. Polar covalent bonds form when nonmetals share electrons unequally. Because the electronegativity of the two atoms is not equal, this creates a more positive and more negative area in the molecule. What are metallic bonds? In metals and alloys, electrons are mobile and move freely. Metals form a lattice in the solid state with a sea of electrons. Metals do not share or lose their valence electrons. The electrons move freely between the atoms. This creates a sea of electrons that surround the positive metal atoms. This allows metals to be strong and still flexible. What are the properties of metals? Because of the sea of electrons, metals have a high thermal and electrical conductivity. They are malleable, able to be hammered into shapes without breaking, and ductile, able to be formed into thin wires. The octet rule. An atom's outermost electrons are known as the valence shell electrons. Only the valence shell electrons are given, taken, or shared in chemical reactions. The group number tells the number of valence electrons. Group 1 has 1, and group 8 has 8 valence electrons. The transition metals, lanthanides, and actinides do not obey this pattern. The octet rule states that having 8 electrons makes an atom stable. Atoms will gain, lose, or share electrons in order to have 8 electrons in the valence shell. So magnesium has 2 valence electrons and is a metal. It will give electrons, becoming positive and a cation. Bromine has 7 valence electrons and is a nonmetal. It will take electrons, becoming negative, and that is an anion. Nitrogen has 5 valence electrons. It is also a nonmetal and will take electrons, becoming negative, so it's an anion. Are there any exceptions to the octet rule? Of course there are. So the first exception is if there are an odd number of available valence electrons and the molecules are unable to form an octet. So one example would be nitrogen dioxide. The Lewis structure for this, so there is an octet or 8 electrons around the first oxygen. There are 8 electrons around the second one, and nitrogen only has 7 because that's all that are available. The next type are suboctets. These are stable configurations that have less than 8 electrons. So BH3, for example. This is what the Lewis structure would look like for BH3. So hydrogen can only have 2 electrons. So each of the hydrogen have a full outer shell, but boron only has 6. Coordinate covalent bonds form when 2 electrons from one atom are donated to an atom that needs 2 electrons to be more stable. Atoms with lone pairs of electrons often do this. So one example would be BH3 plus NH3. These electrons will be donated to BH3. And last, an expanded octet is when compounds have more than 8 valence electrons. So an example would be PCl5. Each of the chlorine atoms have 8 electrons around it, but the phosphorus atom has 10 electrons surrounding it. Lewis structures. A Lewis structure is a diagram of an atom that shows the valence electrons. Each dot represents one of the valence electrons. Remember that valence electrons are the electrons only in the outer shell. To draw a Lewis structure, draw the atom symbol and find the number of valence electrons. Then draw the outer electrons around the atom, starting at the top. Place 1 electron on each side for the first 4. Then add a second electron, continuing in a clockwise direction. So boron, it has 3 valence electrons. So we start at the top and then add the valence electrons around. Potassium only has 1. And neon has 8 valence electrons. So we put 1 valence electron on each side. Then we add a second one until we get to 8. Lewis structures are also used to show bonds in covalently bonded molecules. To do this, draw the symbol of each atom. Where the atoms bond, draw a straight line. This line tells you that the atoms are sharing 2 electrons. Fill in with the extra electrons around the sides of the atom. So the first one, CH4, there are 4 H's around the carbon molecule, and they will each share an electron. So hydrogen has a full shell since it can only hold 2 electrons, and carbon has 2, 4, 6, 8 electrons, so it also has a full valence shell. The next example is CO2. So carbon has 4 valence electrons. Each oxygen has 6 valence electrons, and there are 2 of them. So our total number of valence electrons that we need to show is 16. So we can start with adding a bond between carbon and oxygen, carbon in each of the oxygens. Then we'd fill in with the other 12 electrons. Each oxygen now has a full outer shell. However, carbon doesn't. So in this molecule, we would take 1 pair of the electrons and form a double bond with carbon. We would do the same thing on the other side. So the Lewis structure for CO2 would look like this. Bohr models. Niels Bohr showed that electrons travel in shells. Each shell can only hold a specific number of electrons. Shell 1 can hold up to 2, shell 2 up to 8, 3 up to 18, and 4 up to 32. To draw a Bohr model of the atom, determine the number of protons, neutrons, and electrons. Place the protons and neutrons in the nucleus. Then place the correct number of electrons in each shell, beginning with shell 1. So carbon has 6 protons, 6 electrons, and if it's carbon 12, we have the mass minus the number of protons, and this equals the number of neutrons. So 6. We start at the first shell. That adds 2 electrons. Then we can add electrons starting in the next shell until we get 6. Electron configuration. Schrödinger showed that electrons travel in areas of probability density. Schrödinger's model is the quantum mechanical model of the atom. This model shows where electrons are most likely going to be found. This is a more realistic representation of the atom because the shells are divided into subshells, which are then divided into electron pathways known as orbitals. So the first orbital, the s orbital, can contain 1 pair of electrons for a maximum of 2. This would be written as 1s2 or 2s2. The shape is a sphere. P orbitals can hold 3 pairs of electrons for a total of 6. This would be 2p6 or 3p6. This is the shape for a p orbital. D orbitals hold 5 pairs of electrons for a total of 10. Those would be written as 3d10 or 4d10. And F orbitals can hold 7 pairs for a total of 14 electrons. And this would be 4f14 or 5f14. These are a very complex shape. The larger the atom, the more complex the shapes. New orbitals are built through, around, and on top of prior ones. The periodic table shows this order. An electron configuration is like an electron's address. It tells us which shells electrons are in. Their s and p blocks correspond to the period number. The d block is 1 less than the period number, and the f block is 2 less than the period number. To write the electron configuration, read across the periodic table until you reach the element that you are looking for. Write each of the blocks in order until you reach the element. If you stop in the middle of a block, put only the number of electrons that are in your element. To write the noble gas configuration, write the nearest noble gas in brackets. Only write the configuration after the noble gas. So if we look at oxygen, we're going to we always start at hydrogen. So this is 1s. Here is 1s2. Then we go back and start here. That is 2s2. Keep moving across. This is the p block. So we have 2p and 1, 2, 3, 4. So the electron configuration for oxygen is 1s2, 2s2, 2p4. So plutonium is right here. We look at the noble gas before it, which would be this one. That's radon. And that goes in brackets. That tells you that it has a full address up until that point. Then we would continue. And so we would have 7s2. From 7, it goes to the F block. The F block is 2 less than the period number. So 5F, 1, 2, 3, 4, 5. And that would be the electron configuration for plutonium. Orbital diagrams. Orbital diagrams use arrows to show the spin and the address of an electron. There are three different rules. Aufbau's principle says each electron occupies the lowest energy orbital available. This means you have to follow the rules for electron configuration. You start at the top of the periodic table and read across until you find your element. Hund's rule says a single electron with the same spin must occupy each equal energy orbital before an additional electron with opposite spins can occupy the same orbital. This means place one electron in each orbital before placing a second electron in an orbital. The Pauli exclusion principle says that a maximum of 2 electrons can occupy an atomic orbital, but only if the electrons have opposite spins. The ground state is the lowest energy arrangement of electrons. This is the most stable. Electrons can become excited and jump to higher orbitals. When excited electrons return to the ground state, they emit photons of light. This is what you saw in the flame lab. So give the full electron configuration and draw the orbital diagrams for each of the elements. So lithium is 1s2, 2s1. The electron configuration would be we have 2 electrons in the first shell. They must have opposite spins. And in the second s orbital, we have 1 electron. So that would be the electron configuration and orbital diagram for lithium. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. So we need to show all of those in our orbital diagram. So the S shell, the first S shell is completely filled. The second S is completely filled. The p orbital when we put in electrons, we put 1 up each time. Then we add in the second electron with an opposite spin. Then we have the 3s orbital, and finally the 3p orbital. Okay, so that would be the electron configuration and orbital diagram for chlorine. So if we look at these examples of orbital diagrams, which rules are broken? So the first one, this is the Pauli exclusion principle, which says that there can be a maximum of 2 electrons per orbital, but only if they have opposite spins. So to correct that, we would need opposite spins for each of these. The second one, Aufbau's rule is broken. And this one says that all of the lower energy orbitals must be filled before moving to the next one. For the third one, that's again Aufbau's principle. And finally, Hund's rule, which says that a single electron with the same spin must occupy each equal energy orbital before an additional electron with opposite spins can be added. VSEPR. What is VSEPR? VSEPR stands for the valence shell electron pair repulsion. So as you know, chemical bonds are made from electrons, but only the electrons in the valence shell. Bonding electrons push away or repel other bonding electrons, as well as non-bonding electrons. The repulsion creates the molecular geometry or shape of the molecule. Why? Molecules will have a shape that minimizes repulsion. What about non-bonding electrons? Lone pair electrons are also important in determining shape. Lone pair electrons take up more space than shared electrons. Bonding electrons are pushed together by the unshared pairs. Why is molecular shape important? Many of the physical and chemical properties of molecules are determined by their shape. The shape can even determine if molecules can react or not. So there are several different shapes of molecules. Linear molecules have 2 bonds, no unbonded pairs. It has an angle of 180 degrees. An example of this would be CO2. And the diagram, or the shape, looks like this. A bent molecule has 2 bonded pairs and 2 pairs of unbonded electrons. The bond angle is approximately 109 degrees. An example would be water. These unbonded electrons take up much more room than the bonded electrons, and so the unbonded pairs push the bonded pairs of electrons towards each other. Next is trigonal planar. These are 3 bonds. There are no unbonded pairs. The bond angle is 120 degrees. One example would be BF3. That's the shape of a trigonal planar. Or the next shape is tetrahedral. So there are 4 bonds. There are no unpaired electrons. This has a bond angle of 109 degrees. And one example would be methane, or CH4. So with this drawing, the lines represent atoms that are flat on the page. The dotted lines represent a molecule that is going back into the page, and the wedge is a molecule that would become, or an atom that would be coming out towards you. The last shape is trigonal bipyramidal. So this has 5 different bonds. There are no pairs of unbonded electrons, and it has 2 different bond angles, 90 and 120 degrees. So an example of this would be phosphorus pentachloride, or PCl5.